In this video, we're going to take a look at Newton's laws of motion and also gravitation. And this will be our first introduction into gravitation, so we'll go a little ways with it and continue on more in our study of gravitation in future videos. His birth date has two different dates there. The year he was born, it was 1642. He was born on Christmas Day in 1642. But later, England switched to the Gregorian calendar from the Julian calendar, and a lot of times you'll see past dates revived for the modern calendar. So on the modern calendar, he was born 11 days after Christmas 1642, which put him into 1643. During his life, he developed the laws of motion and gravitation. He studied optics, he studied mathematics, he developed calculus. Simultaneously, there was a German scientist or mathematician named Leibniz who was doing it. A lot of his scientific work was done in his 20s, and he just kind of sat on that for a long time. I'll mention a little bit about that later. He later headed the British Mint. Now, so far, what we've learned about are Kepler's laws of planetary motion. And we're going to call these things of Newton's laws as well. Some people have the idea that a law is the most advanced thing that there is in science, and that's not actually correct. A scientific law is a statement based on repeated experimental observations that describes some aspects of the universe. It always applies under the same conditions and implies that there is a causal relationship involving its elements, but it doesn't state necessarily what the causal relationship is. Kepler's laws just make the observation that, among others, planetary orbits are ellipses. That's just based on the observations. That's the shape of them. There is no why behind the fact that they're ellipses. They just are. Newton's first law of motion. For the most part, it was developed by Galileo, although Galileo had a little bit of an incorrect idea that I'll mention here. An object will remain in a state of rest or uniform motion unless it's acted on by an unbalanced outside force. Now, uniform motion means constant speed in a straight line. At least when Newton came to it, it did. When Galileo stated it, he thought something moving with constant speed in a circle could be uniform motion. With Newton, it had to be a straight line, constant speed is the uniform motion. The unbalanced outside force is a push or a pull, something which acting alone would make the object change its motion. If you have an object sitting on a tabletop, it has outside forces acting on it, but they're not unbalanced. The table is pushing up on it, Earth's gravity can be pulling down, and those are balanced forces. So they have to be unbalanced in order to take it out of uniform motion. You need to trust this law if you're driving in the wintertime. Trust that your car will keep moving in a state of uniform motion unless you have friction between your tires and the road to stop your car. So don't test Newton's first law on an icy road, because the first law is going to win. Newton's second law of motion had to be a second one if they were going to bother numbering them. I like to see it written this way. You'll also see it written in another way, but when it's written this way, you have the impression that a force acts on a mass. F is for force, m is for mass, and that produces the acceleration. And so the acceleration of an object will be the force acting on it divided by its mass. Mass is a measure of how difficult it is to accelerate something. That is, speed it up, slow it down, or change its direction. Most of the time, you see Newton's second law written as F equals ma. That just kind of rolls off your tongue. But people see that and they sometimes think, okay, so you have a mass and you give it an acceleration and that produces a force on it. That's not right. It's the force you put on the mass that causes it to accelerate. So keep that in mind. This looks easy. It's actually the net force acting on the object, and sometimes you have to do a lot of work to figure out just what the different parts of the force happen to be. So not so simple in every case. Then Newton's third law of motion, I would guess many of you could rattle off something about it having to do with for every action there's an equal and opposite reaction. When you get to defining an action and a reaction, you may be challenged. Here's the third law of motion. When one object exerts a force on a second object, the second object will at the same time exert a force back on the first object. The reaction force will be equal in size but opposite in direction. All forces are interactions between objects. We'll consider this when we look at things like the motion of the moon around the Earth a little bit. Where we really consider this is when we start looking at exoplanets and determining the masses of planets and stars. Okay, your book does a reasonable job of discussing Newton's laws of motion, so we're not going to spend any more time on them than that. On to gravitation. Kepler had thought that there was some sort of a cause for the planets orbiting the sun, and he thought that Earth must exert a force on the moon that keeps it in orbit around it. When Galileo discovered the moons of Jupiter, he thought there was some sort of a force that Jupiter exerted on those moons, keeping them in orbit, and Kepler thought that the sun must do some sort of a force on the planets to keep them in motion around it. Galileo discouraged Kepler from pursuing this idea. For Newton, though, if planets and moons traveled in ellipses, there must be a force acting on them. Otherwise, they would travel in straight lines. And so he started developing this idea of gravity. And that force is what we call gravity. So here's the law of gravitation stated verbally. Between any two objects with mass, there is an attractive force. The force is proportional to the product of the masses and inversely proportional to the square of the distance between the centers of the objects. This may start getting kind of confusing when you see it that way, so we'll write an equation for this. Newton developed this while he was in his 20s. He was sent home from college just about as soon as he graduated. He would have stayed studying there, and the reason for that was that an epidemic of the plague hit Cambridge at the time. And so the college was closed for 2 whole years. They didn't have internet classes in those days. While he was at home, he started thinking about a lot of these ideas and developed many of them. Then he didn't publish it or publicize it at all, and nobody knew about his work for close to 20 years. His work with gravity finally came out because of an offhand question by Edmund Halley. Halley encouraged Newton to write up all this research he'd done, and he finally did a few years later. He had to finish his work with calculus in order to complete the development of his law of gravitation to his satisfaction. Here's the equation form of it. The force between two objects with mass is going to be that G, capital G there, is called the universal gravitational constant. It's got one value in the metric system and a different one in the system that we use in the United States, although I have never used the American system units for looking at gravitation. I don't know if anybody does really. Just about everybody who uses it would use the metric system. Anyway, it's a proportionality constant is what it is. Then m1 would be the mass of one of the objects, m2 is the mass of the other object, and r is the distance between the centers of the two objects, and that r is squared. So a few things about it. It's between any two objects with mass. planets, books on a tabletop, people. However, it's a weak force. It is by far the weakest force in nature, and the only way to get an appreciable force from it is to have one or both of the two objects be very massive. The r stands for the distance between the centers of the objects. It does not necessarily mean a radius, although sometimes it is, and we're going to look at some examples where it does happen to be a radius. If you're talking about the force between the Earth and the Moon, it's the distance from the center of the Earth to the center of the Moon. So that's not the radius of the Earth or the Moon, it's the radius of the Moon's orbit. And then the g, just a proportionality constant. You could invent units where g would have a value of 1. Okay, now why these laws matter, the motion and gravitation laws. They're universal. They work everywhere. At one time, people thought the rules in the heavens, out in space, must be different from the rules on Earth. Newton said, nope, they're universal. They follow the same rules objects here on Earth do. They let us understand and predict the motion of all sorts of astronomical objects, and they give a why to Kepler's laws. Kepler developed the laws. He said, this is what the planets do. With Newton's law of gravitation, you can say, this is why the planets do what they do. However, we still didn't have a why to gravity. Why is there this force that depends inversely on the square of the distance between two things? Maybe there will always be that sort of a why when we develop these things. Einstein went a bit farther with gravitation. The more correct version of gravitation that works in more situations and better is Einstein's general theory of relativity, but it is, as they say, beyond the scope of this class. So we're not going to take a look at much of it, except maybe for a couple things. One other thing about the laws being universal, it means that the force from the sun is not the only force acting on a planet. The other planets exert forces as well that can cause subtle effects and sometimes not so subtle effects. Jupiter often severely changes the orbits of comets. Sometimes Jupiter even captures comets, so they end up orbiting it. And in summer of 1994, one of the comets that Jupiter captured actually crashed into the surface of Jupiter. That was kind of a neat thing to see through a telescope. Earth and Venus exert forces on each other that have put Venus into a sort of a gravity lock with Earth. The rotation of Venus is such that every time Venus catches up to and passes the Earth, at the moment of closest approach, the same point on Venus always faces the Earth. And that's because of a force going on between Earth and Venus. So we can't ignore interplanetary forces as well. So these laws give us the reasons planets, comets, and moons behave the way they do. And lots of other things too.